Welcome everyone. So I'm going to talk about this slightly controversial topic. There's a lot of heat in the industry in terms of this discussion. So what I'm going to talk about to you today is the study that I did over the course of a couple of years, analyzed tens of thousands of pull requests, and I'm going to share with you some systemic insights that I got out of the study. Some of the insights have been expected, something that was intuitive, and some things were surprising for me, so I'm here to share it with you. So I work as a principal engineer based in Berlin, and the fields of interest of mine throughout my career have been XP, so I'm a XP practitioner, extreme programming, theory of constraints, linear systems thinking. And these days I'm kind of trying to connect the dots between these fields. There's a lot of really interesting overlap, and I'm kind of enjoying that journey. I tend to rant on social networks if you're interested to connect, and there's something, this is mostly related for the Italian audience often, but there's one fact about me is that I put mayo on pizza. So not sure how many people have heard for this quote, nobody ever got fired for buying IBM. But during 80s, IBM was a really big vendor, and if you were working in a procurement department, you had a lot of questions to answer if you didn't go with IBM. So there was a lot more scrutiny if you chosen some other vendors, and the reason for going with IBM at one point became because it's kind of a strategy for minimizing the downside risk. If anything goes wrong, hey, who could have known? You know, it's IBM. Everyone else went with them, so it's very also easy kind of to hide in a sense. And when I think about this quote and I think about the ways of working, I would say north of 95% of the teams that I get to see and observe, in terms of the ways of working, this is usually the visual that I have in my head. So I call this PR-based async code reviews, and I'm quickly going to go through the visual just for the folks that are not too familiar with it. But it involves something about PRs, which is pull requests, and something about the async part, and something about the code reviews. So here we have two developers, Emma and Luca, and let's say it's the start of iteration, and they are working. I used to say individually, but I'm going to switch the language. I'm going to say they work in isolation. So they work on their own tickets, so to say. So Emma pulls ticket number 1. And Luca pulls in ticket number 2. So if you focus on Emma's part, she is doing some coding, changing the system, implementing a feature, and at one point she figures out, okay, I would like to invite my peers for a review. So I'm gonna raise a pull request and I'm going to invite Luca for a review. But Luca is busy. So Luca is working on ticket number 2, and there are a bunch of other things that are competing for his time, reviewing other PRs, other meetings, email, Slack, etc. And he's not able to react immediately. Emma, knowing that and not wanting to be a lazy employee, what she does is she figures out, okay, I think I can start working on something else. So she pulls in ticket number 3. At one point, Emma figures out that Luca is not responding, so she reminds him, and at one point Luca comes around, reviews a PR, provides some feedback, asks for some changes. They go back and forth until they converge on a solution that both of them are satisfied with. The pull request gets approved and merged. So that's kind of the life cycle of ticket number 1 here. The same thing happens for any other ticket, by the way. So this is a 30-minute talk. It's a half version of my 1-hour talk, and I'm going to give you the most important parts of that. And if there's one thing that I would like to take with you, it's that async by design means delays, right? So I'm not saying that you shouldn't do it per se, but I'm saying that you have to be really aware of the fact that if you're designing a processes which involve way of working, which involve async interaction, then there are delays always by design. If there were no delays, it would be sync. So the study involved, as I mentioned, more than 40,000 pull requests now, and the context is typical product development teams, right? So no open source software, usual teams that we get to observe. co-located either physically or virtually, but they're kind of working in the same or similar time zones. And the things that I was curious to understand a bit were these three things that I'm going to talk about today. So engagement, wait time, and size. And I was curious to understand also the relationship between these three. So let's go into the first one, which is the engagement. So why was I curious about the engagement? I was curious about it because I was trying to understand what are the effects of the delayed communication that we get to see in async code reviews, and also the understanding of the impact, the second, third, and nth order effects of the choked feedback. Now, the metaphor that I had in my head, when I have a conversation, when I have a call with someone and there is a delay involved, what I notice is that the conversation tends to die off pretty quickly because we're responding to some previous requests or previous part of the communication that we had. And the other thing is also that in the pull requests, we usually or most often provide feedback in a written form, which has a very narrow bandwidth, so to say, as a medium of communication compared to when you're talking to a human and also having a sync interaction with them, right? So the expense also of the feedback is kind of higher, but this was kind of the starting ideas, or why was I interested in engagement in the first place. So there's the reason why I also call this way of working a high latency, low throughput feedback. And if you go into the first scatter plots on the x-axis here, I'm not sure if everyone is able to see, but we have size in lines of code. And I've chosen this metric as a proxy for the amount of effort that individuals tend to invest. It's a good approximation for some cases, for some not. And what I'm going to talk about here today is mostly for the ones that it was a good fit as a proxy metric for the amount of effort. Then on the y-axis, you can see the engagement, and engagement is the number of non-trivial comments that they get to observe on the pull request. And non-trivial, the way that they define it, is a comment that is not trivial, and a trivial comment is a comment that is 4 or less words. Now, why was that the reason? Because I wanted to filter out all of those looks good to me, +1, thumbs up, LGTM, etc., which don't really provide value for the other side. So what can we see here? Not much. Most of the things are kind of in this lower left side of this data set. I think this is around 500 merged pull requests. And the things that they observed that I'm going to show today have been observed in all of the data sets for the teams that have been doing async code reviews. And there's one really interesting question to ask in this case. It is, let's say that you invest a week and you produce a pull request that is, let's say, 1,000 lines of code, and you get, I don't know, 2 comments back, right? Is it the same thing and compatible when you invest, I don't know, half an hour, 1 hour, and you get back 2 comments? So I was curious to understand how does the y-axis look like if we normalize it by size. So here you can see the number of non-trivial comments divided by 100 lines of code. So, and this was kind of interesting because what you get to observe is that as you increase the size of the pull request, the engagement per size tends to go down exponentially. And this was honestly not surprising for me. I think most of developers or most of the people that are working closely with the team tend to observe these big pull requests where you just, after a week of work, I cannot do anything about it. So I cannot course correct, I cannot build in quality. Providing feedback is going to take a long time, and we're going to have to go back and forth for a long time until we converge on a solution that all of us are satisfied with. So I just say, looks good to me, approve it, and then deploy it to production, and I hope that nothing is going to break, which is often not the case, or if it doesn't break at that point, we kind of pile up cumulative risk over the time. So I'm not sure how many people also observe that 500 lines pull request looks good to me, 50 lines of code, 10 comments or so, right? So it's interesting because when you think about the whole thing about the code review and the pull request is that we're trying to use a human judgment to build in a human judgment in the delivery process in order to be able to build the quality in. But if we're saying that we're not on some parts of the spectrum of the pull request we're not even able to get the feedback, then that's, which is a precondition in order to be able to build in the quality. Then if we're not able to get the feedback, that also likely means that we're not able to build the quality that we wanted in the first place. So we have both the delays and also a lack of quality. I'm not saying anything about the left-hand side. I'm not saying that if you have lots of feedback that it means quality, but I'm mostly saying the other way around, right? And let's go now into the wait time. Here the things were kind of a bit more surprising and also interesting. So if you focus on ticket number 1 here, the thing that you might have observed is this thing at the bottom of the screen. So here you can see a cycle time or life cycle of this whole ticket, and you can observe some parts that are yellow and some parts that are gray, and the gray parts are the wait time. So the wait time is, or queue time, also a metric that comes from Lean. The idea is that you try to figure out where the most of the wait time happens, in a sense that it's a time where this item is just sitting in a queue waiting for someone's attention. So waiting for Emma to respond to Luca's feedback, or Luca to review a pull request, etc. Right? And interesting thing is just sharing one of the data sets, and is that, for example, for this one, 500 merged pull request, for this team it took them 6 months to push through the system of work, meaning from the start of the full first pull request until the merging of the last. And what was interesting was to observe that the cumulative lead time was close to 28 months. So it's a really good conversation starter. These numbers are not precise per se, but the order of magnitudes are something that are really interesting to observe and talk about as a team. And if we focus on now on the wait time, so x-axis size and lines of code, and then the y-axis is wait time in hours. Interesting thing here is that this thing looks very kind of uniform, so to say, but if you think about it, if you have a pull request that, I don't know, you have 500 lines of code and you invested a couple of days or a week in developing it, and then you wait for feedback for 2 days, it's not the same thing as when I make a small change, I don't know, 50 lines of code, and I have to wait for 2 days, right? Let's say that I invest 1 hour, right? Why? Because the wait to processing time ratio, the wait time in relation to the unit of effort, is different, right? And if we normalize the wait time per size now, on the y-axis, and we show the minutes of wait time per lines of code, what we get to observe is that as we reduce the size of the pull request, if you keep working in the same way, which is async code reviews, the wait time per size goes up exponentially. And it's interesting also because we get to see also the reasons. One of the reasons for that is that people get more engaged for the smaller pull requests because they have a sense that they can build the quality in, right? But the feedback for the smaller pull request, the delays are way more expensive per unit of effort than for the bigger pull request. So if you reduce the size of the pull request, but you're not reducing the wait time per unit of effort at the same time, what you get to observe is that you get to incur more waste in the whole process. And so one kind of implication of that, my understanding of this curve that I got to observe, was that actually the cost of code review per size goes up exponentially as we reduce the size of the pull request. And I'm pretty sure that all of us want to have small pull requests, and this is usually the intervention that I do with teams when I coach and mentor on these topics. If you have a huge pull request, reduce the size of the pull request. Why? Because they take less time to write, right? They're also quicker to review. I can squeeze in reviewing smaller pull requests way more easily than trying to review a pull request of 1,000 lines of code. They tend to have higher engagement, which are preconditioned for higher quality. They're also less risky because we're changing less things at the same time. Easier to troubleshoot where something goes wrong in production. We can pinpoint easier, and they also positively contribute to all 4 DORA metrics. So we want to have a small pull request, but then there's this trade-off, right? The trade-off is the increased cost of code review per size as we're reducing the size of the pull request. So One of the similar examples that especially developers might have observed of the system pushing back against you, increasing the cost of doing the things, is, let's say that if you have a test suite that takes 20 minutes to run. If you have a test suite that takes 20 minutes to run, you're not going to run the test suite after every line of code change. Why? Because it doesn't make any economic sense. So what the system is telling you, hey, getting feedback from tests is very expensive if you reduce the size of the changes, if you try to run it more often, so use it very wisely. So what I'm going to do, I'm going to increase the amount of changes that I introduce before running the tests, which means I slide back into the bigger batches and I incur all the problems that come with it that are inverse compared to what we saw on the previous slide with the smaller pull requests. And this is also the reason why I really love this quote from Don Reinertsen: while you may ignore economics, it won't ignore you. So be very careful about the economical incentives that you're trying to introduce with your teams when you're trying to change the ways of the working. Switching gears now, going into the flow efficiency, I'm pretty sure at least some percentage of the crowd is familiar with it. But the idea of flow efficiency is that as we look at the cycle time of the work item, then we try to figure out how much of its cycle time we spent effectively working on an item, right? And the lower the flow efficiency, the more wait time, the more waste you have in the process, because this thing is just sitting there in a queue waiting for someone's attention. So you want to improve the flow efficiency by driving this number up. And one of the interesting scatter plots that we can also observe here on the y-axis treat this thing as a flow efficiency. I'm not going to go too much into the details what exactly it is, but you can treat it that way. What we can observe is that at one point it starts plummeting. So here maybe around, I don't know, 120 lines of code or so, right? There's really interesting thought experiment that you can make at this point just looking at this line. Let's say that you have a 300 lines of code change that you want to push through the system of work. And let's say that you have at least 2 ways to do it. One way is splitting these 300 lines of code change into 15 PRs of 20 lines of code. And the other one is 1 PR of 300 lines of code. Comparing these two things, having in mind this line, which one do you think is going to cumulatively take longer time to push through the system of work? So it's the ones with the smaller pull requests, right? Because you're incurring way more waste per unit of effort, having observed what we observed. So what we're saying is on the lower end of the spectrum of pull requests, we're losing the throughput, right? So on one side, we're losing the quality, we're not being able to build in the quality, and on the other side, we are losing the throughput. So if you're doing async code reviews, then you have to make this trade-off. Do I lose the throughput or I lose the quality? And anyone that has read the Don Reinertsen's book, The Principles of Product Development Flow, you might remember this batch size optimization U-curve, where you have these trade-off forces, the transaction cost and the holding cost. And we're talking here, when it comes to the wait time, about the transaction cost. What you're effectively trying to do is you're trying to balance these forces to find the optimal batch size. And this is an interesting thing, right? Because as I was kind of getting more senior as an engineer, so to say, I noticed I started talking more in terms of the trade-off, and there's always a trade-off, right? And I think that's true, but that doesn't have to mean that you're not able to change the trade-off forces in a way to get even a win-win. So the interesting thing is that you can affect some of the trade-off forces that is going to help you out with the trade-off not looking as a trade-off. What that means is that we're going to get into it soon, so I'll talk about it. One kind of for anyone that has read the accelerated book, which is about the results of the Dora research, I think the biggest myth, at least for me, that was debunked through the accelerate was it's not either throughput or stability, but it's either both throughput and stability or none of those, right? So you cannot have higher stability if you don't have higher throughput and you have smaller batches where you invalidate the assumption sooner. So what I'm trying to say is that we might have our cake and eat it too. So in terms of the problems that we observe, right? So what we say is that as the cost of code review per size is going up, then as we reduce the size of the pull request, we're losing the throughput, right? So what are the things that we can do if we don't want to lose the throughput, but we still want to reduce the size of the pull request, right? So we want to have this essentially. So let's work backwards. So in order to not lose the throughput as we reduce the size of the pull request, the cost of code review per size must not go up as we do that. And in order to do that, the actors' reaction time, where actors means authors and reviewers, has to go exponentially down, meaning they have to react to each other's request faster and faster and faster as we reduce the size of the pull request. And in order for them to be able to do that, their availability needs to go exponentially up, which essentially means they have to reduce the working process, right? In order to be able to be responsive to each other's requests. Now, if we pull up this ticket number 1 here and just show it on the timeline, and let's say that this team has this average size of the pull request, what essentially we're trying to say is that as we reduce the size of the pull request, they have to react faster and faster and faster in order not to lose the throughput as they do that. To the point that at one point they're going to need to start working together in order not to incur this exponential increase in the cost of the reviews. And that was the conclusion of the study. In order not to exponentially lose the throughput while reducing the average size of a PR, people need to get exponentially closer and closer and closer in time, which essentially leads us to a continuous code reviews. That's kind of a portal to parallel universe. Just curious, how many people here are working in teams where developers are mostly working in a pair or mob and ensemble programming? Just curious. Okay. So I jointly call these patterns co-creation patterns. There are a couple of other names out there. But what's interesting, I'm going to talk about these practices only in terms of the story that preceded this part, is that essentially we are changing the economics of the system. Why? Because with working together, we have the guaranteed availability of the reviewers by design, right? So the wait time is essentially 0, right? So what happens is that you're able to reduce this transaction cost all the way to the left, so to say, to push the optimal batch size all the way to the left. So at this point, this trade-off, there is still a trade-off, but it doesn't look as one anymore, right? Because you're able to influence one of the forces to push to the other side. So what are we trying to optimize for here? So we want to reduce the size of the pull request. That's something that it's kind of non-negotiable thing, so to say. We want to reduce the wait time per size, and we want not to lose the engagement per size and reduce the size of the pull request. But it's usually this engagement, as you reduce the size of the pull request, as you also saw, it kind of goes up because people have a feeling that they're able to intervene and course correct. So if we put these 3 things into one single formula, so to say, we model this relationship, I came up with this just one number called PR score. It gives you one of the ways or angles at looking at the whole process. So it's size times wait time in minutes divided by 1 plus engagement. 1 plus engagement because engagement can be sometimes or often 0, so no feedback given, and you don't want to divide by 0. And what's interesting thing here is that when you think about when people work together, the size of the pull request, so to say, is a minimal, is atomic change that is reviewed immediately in a sense, right? It can be as small as 1 line of code that you're changing. The wait time in minutes is 0 because it's instant, and the engagement doesn't matter, but usually goes up. And this whole thing evaluates to 0 in a sense. So what I'm trying to say, if you're optimizing for these 3 things, then this tends to be the results that you would want to strive for. And this is also one of the reasons why I often say that the optimal size of a pull request is 1 line of code that is reviewed as it's being typed. And I honestly don't know of a better way to achieve it yet than by pair and mob programming. If we happen to discover some other practices, I would be really curious to know about it. So when we chart or plot these pull requests that have been done in the async code reviews, here on the y-axis you can see score, but this is, by the way, on a log scale, because the numbers were so bad, so to say, that I have to put a log scale, and this is one world that I get to observe. And then there's the other world of continuous code reviews, co-creation patterns working together, and this gap here is the distance between these two worlds, so to say. So throughput or quality, I often say both throughput and quality. We kind of try to always look for these trade-offs in a ways that are, I mean, there are ways to look at the trade-offs that could be more helpful than what we usually often get to observe. And with that, I would like to thank you. I wanted just to mention this article that I wrote for InfoQ 2 years ago or so, that got quite a lot of traction. It expands on this talk and introduces some other things related to the co-creation patterns. So if you're interested to learn more about that, you can visit that. And that's all. Thanks for
Thank
attention.
you.